today's session is GraalVM in a nutshell, and we'll focus on how to build fast, small, and efficient, cost-efficient Java applications. Let me start the timer. Okay. So just for context, before we jump into today's topic, there are a lot of activities going on in the Java ecosystem within Oracle. So we have the OpenJDK that a lot of you are familiar with. The OpenJDK focuses primarily on the Java language and the Java platform itself. And then we are from the GraalVM unit, and the GraalVM unit focuses more on compiler optimizations, compiler technologies, and so on. So that's how the OpenJDK is more about the platform itself and the language, and GraalVM is more about the compiler technologies and innovations around it. So there are two modes of GraalVM. The first mode is just-in-time compilation. So what I mean by just-in-time compilation is you're taking, basically GraalVM has a JDK, and it's a drop-in replacement for your OpenJDK or Oracle JDK or any other JDK that you have. So you install it on your machine and just set the Java home, and then you can run any Java application on this using Java -jar. It'll pick up the Graal JIT compiler, and then you'll get all the benefits of the optimizations out of the box. So better performance out of the box. But the focus of today's talk is more about the ahead-of-time compilation. And that is available with GraalVM Native Image. So we'll look at that. I've shown a small command here, which is, this is you take your jar file, you run it against the Native Image command, the tool that we have, and you get a binary at the other end. So binary with machine code, and you can run that binary directly on the directly. So two modes of GraalVM. One is the just-in-time compiler, which is when you run your application on the JVM, and second is Native Image, which is the ahead-of-time compilation, which you either run on your desktop or you can run it in CI/CD pipelines. So how does it like what exactly happens? GraalVM takes in, Native Image actually takes in bytecode. So you can give your jar files, your application class file to GraalVM Native Image utility. And on the other side, you will get binaries which are platform specific. So if you're running it on a Linux machine, you'll get a Linux binary. Similarly, you'll get Windows and Mac OS. And what people generally see is fast startup time. So really fast startup, and less memory, a lot less memory compared to traditional JVM-based applications. I'll dive a little deeper into what happens in the Native Image utility. So in terms of inputs, we said that you can give any bytecode. So you can give your classes, jar files, etc. So you give your application, run it through this Native Image build tool. Your application will have its own classes. You will have third-party libraries. You will be dependent on the JVM classes which are included. Plus, there is a substrate VM, which is a Java-based VM, which is provided by GraalVM itself. And this has the memory management capabilities. So, for example, it has things like garbage collection, etc., baked inside. Once you give this input, what Native Image utility does at build time is it does a static analysis of your code. So it will start from the main. So if you have a main in your program, it will start from there, and it will look for classes and methods which are being called from the main. This is all statically happening at build time, right? So it'll go through the entire traverse. It will traverse through the entire chain. Whatever is reachable at build time, it will go and look at all of those. So if a class A method X, for example, is calling class B method Y, it'll trace the whole chain through and through. Along the way, it'll run some static initializers as classes are loaded. It'll run the static initializers. It'll create new objects on the heap. And then what we do is we do a heap snapshotting. So whatever is populated in the heap is snapshotted and captured in the native executable. So at the end of it, the native executable has two things. One is ahead of time compiled Java code into machine code. So you have the machine code for your Java classes, and then you have the image heap, which is snapshotted. So whatever classes were there whatever objects were there in the heap are snapshotted. And then you get platform binaries for ARM machines or for the x86 version. So you'll have both. So what are the key benefits of native image, right? Why do we recommend people use native image? So there are 4 key value props. One is the memory efficiency, and you'll see it in the demos, like why memory consumption is reduced significantly. Startup is excellent. Startup time is really fast, and the other 2 advantages are we reduce your attack surface significantly, so that your application binaries are safer compared to a traditional JVM application. And the size of your binaries are very small, so you can package them in small container images. Let's start with memory efficiency and startup. Let me switch to VS Code. And just to save time, I've just got the commands. I'll explain those, and I'll also show you some scripts. So this is a simple Micronaut application. Let's see, it's connecting. Okay, great. So my code is actually running in the cloud. This is a cloud machine. I've just used VS Code Remote SSH plugin to connect to it. This is a simple Micronaut application with a main here. I've got a simple REST controller. All it's doing is there is a hello REST endpoint, and if I send a request to this REST endpoint, it will respond with hello world. It's a simple application, but it's good enough for me to demo the benefits of native image. So I think what we'll do is we'll start with how to convert this simple application into native image. So we have within GraalVM, we have native image also has Maven and Gradle plugins which are available. So you can directly include them in your build files. So I'll just run this and I'll explain what's going on. This Maven, I'm running Maven package with packaging type as native image, and then I've got a profile in my pom.xml. I'll show you what that profile looks like. This native image build on my machine, on the cloud machine, will take about 2.5 minutes. Meanwhile, I'll show you what is included in the pom.xml. So I think this is a simple Micronaut Hello World REST application. So I'm using Micronaut 4.2. Micronaut 4.2 is already compatible with native image and supports JDK 17 and 21. I'm using 21 here. 17 and 21 are the latest LTS releases, right? 21 is the latest. Okay, and then I think if I scroll down a bit, I'll show you, these are all the dependencies that Micronaut needs, but I'll show you the profile, right? I told you I'm using a native profile. And here, if you see, I'm using the GraalVM build tools, the native image Maven plugin. Similarly, we also have a Gradle plugin. And I'm using the G1GC as the garbage collector. Right? The same thing we'll use for the JVM based application as well. And then I'm also generating a SBOM. You don't have to worry about SBOM right now. We'll cover it in the when we talk about security. Okay. So when I run the native image build, it's doing a bunch of things. Everything here is clickable, right? So if I click on this, it'll take you directly to the corresponding documentation page, and it'll tell you exactly what each of the parameters on the screen are, or what the my target machine is x86 because I'm running on an AMD 64 cloud machine. If you don't give profiling hints to the native image compiler, there is a machine learning based inference that's going on. So that's saying PGO is ML inferred. And then if you look at here, right, down here in this section where it's performing the static analysis, out of a total 15,575 classes, it is only 88% of the classes are reachable. Similarly, out of 34,700 fields, only 58% are reachable. And similarly, out of these 116,000 methods, only 63.5% are reachable. What does that mean? Is anything that's not reachable at compile time, at build time, will be removed from the executable. So the code that is in your executable is only what is required or what is reachable at build time. Okay, so it has finished the build, and it took about 2 minutes and 35 seconds. And then this is where it'll tell you about 50 MBs in the code area, about 30 MB, if you all can see that, 30 MBs in the image heap and so on. The total binary size is about 82 megs. Then it'll show you things like what are the top classes and packages that have been included in the code area and so on. Okay. So I've run this. Now let's go back and we have a start for measuring startup time. I have this start script. I'll show you the script. Let me run this. So the startup script is it's a simple, I'm just selecting the command. If I pass native, it will run the native version. And then all I'm doing is I'm waiting for the localhost 8080 endpoint, hello endpoint to be available. Once it returns 200, I'll stop the process and return the response back. This is for native image. I'll also run the same thing for the JDK or the JVM version. So let's do the standard Maven package. Maven package is just building a jar. I want to show you side by side, so that's the reason I'm just doing it. And then I'll run the startup script. Startup script with JVM as the argument this time. Then we can compare both side by side. So now if you look at this, so if you look at the native image one, it starts in about 25 milliseconds. I'll just put it here. These are from previous runs, but I'll just, so native image starts in about 25 milliseconds. The JDK one or the JVM one starts in about 621 milliseconds, right? Then if you look at the number of CPU instructions which were run in both the cases, we look at the, this is the CPU instruction. I'm just comparing them side by side so you all can see the benefits. This is, we put some commas here, 2 million CPU instructions in case of native image. And if you look at the, this is, I think, about 9 billion, roughly about 9 billion, I think this is. Yeah, this is about 9 billion instructions in the JVM case. And then if you look at the user CPU time, which is how much time your user code was, how much CPU time was given to your user code. It's about 23 milliseconds in native image and about 2.5 seconds in the case of JVM, right? So if you look at the benefits, right? Like if you look at it, the startup time is about 25 times better in this case. And you will see similar results in other applications as well, right? When you run it on JVM versus running on native. And you see the other things as well, the number of CPU instructions that are being run compared to native image compared to JDK. Okay. So this was about startup time. Then I think let's go and quickly run the memory one. So for memory, I've got two flavors. Oh, sorry, let me run this one, which is, I'm going to run the same command, but this time it'll run for 20 seconds. 20 requests, not 20 seconds. So I've got this file called record.sh. I'll show that. Let me put it here. This will run for about 20 seconds. It's the same script again, but instead of calling it once, I'm running it 20 times. So it is like sending some little load to this application. This one, and it'll spit out some plots, so you can see what the memory and CPU utilization was. Here I'll run the native version. Wait. 1 second, I'm just losing my screen here for 1 second. Okay. Let me just copy. So here we'll run the native image one, and it'll run for about 20 seconds. And then I think what you will see at the end of it is you will see two plots, right? So once that finishes, let me bring up the first plot, which is the this is what you will see in the JVM case, and then I'll show you what you will see in the native image case. So let's put it side by side so you can see the difference, right? Like, is this clearly visible? Yeah, so on the right is your JVM, right? So when I run the same application as a Java minus jar, you can see the blue line is the memory consumption, the red lines are the CPU consumption. And this is traditional JVM, right? Like when you start to boot up a JVM application, you will see a lot of activity going on. We'll see it in the couple of slides. And then the JVM, if you look at the memory, it's increasing initially, and then at some point, once the warm-up has happened, it will stabilize, and then you will start seeing peak performance, right? And then that's the peak memory that's being used. So about 200 megs in this case. And similarly, if you look at the native image, the memory starts up, like a small one, and it's almost constant throughout, right? This is obviously, I mean, I'm just sending 20 requests, but you'll see a similar pattern if you run it for longer duration as well. So memory is about half. In this case, memory is about 100, less than 100 megs. In this case, it's about 200. So memory is about 50%. If you look at the CPU utilization, there's not much going on in the native image because there is no JIT compiler running. There's no profiling happening. A lot of things are not happening in the on the left-hand side, right, in the native image case. So let's switch to the slides. So let's look at what's happening in terms of memory requirements in both the cases, right? So we have the same garbage collector in both. So we have G1, GC in both the cases. On the left-hand side, in the JIT mode, we have the hotspot VM running, and along with that, we have a JIT compiler that's running behind the scenes. So that requires memory. On the right-hand side, in the AOT case, we only have the native image binary, which will be loaded into memory. So that's only machine code that will be loaded directly into memory. There's no JIT compiler, there's nothing. Both the applications will be creating objects on the heap. So they'll be using memory for that, which is fine. And then in addition to that, you have a lot of things happening in the JIT space, right? So for example, you have the meta space, which is where all your jar files or bytecode is being loaded. So that needs some space in the memory. You have the JIT compiler and profiling that's happening behind the scenes. So that needs some memory to keep track of what's happening, which classes are hot, etc. The compiler itself has some data structures which is using for compiling. And then the last one is the dynamic code cache, which is the machine code that's been kept into memory for the hotspot keeps some hot code into memory. And if the code is no longer hot, it has to take it out and put it into interpreted mode, and then load something else into the memory again. So it has some cache. So these are the additional requirements that the JVM has, which are not there in the ahead of time compilation. Then if you look at the startup time, if you load the Java application using jar files, first the JVM, this is what happens on the boot, at boot time, right? So you load the jar files, they are uncompressed, they are verified, then they go into the interpreted mode. Then there is a profiling that's happening to find out what's hot versus what's not. The hot code is compiled into machine code and then kept in cache. And then you start seeing the peak performance. So if you remember that this thing on the right, all the red and the peak memory is all, these are the things that are happening at that point in time. Whereas on the right-hand side, if you look at it from a native image perspective, we already have the machine code. All we have to do is load it into memory and then execute at peak performance. That's what you saw here, right? So when we went here, the memory remains constant. There's no CPU utilization that's going on when JVM boots up. Okay, so now let's look at the throughput quickly. I'll go back to this. So for the throughput, here I'll be sending 1 million requests. I think what we'll do is, so this takes some time. So I think we can, I'll show you what the script looks like, right? So we're running perf to capture some data and then waiting for the 200 for it to start up. and then firing a million requests using this tool called Hey. So Hey is like a load testing tool that we're using here. And I think once it's done, once the demos are done, we'll breeze through the slides. So I'll give you a quick dump of what's happening behind. So one part is done. Let's do the same thing for the native image side. There is also a concept of an optimized native image. What I'm showing you right now is the out-of-the-box capability with the default machine learning-based inference. There is also an optimized one. If there's time at the end, I'll show you that. Otherwise, we can, we can talk about, for people who are interested, we can talk offline on that, because I may be running out of time. So let's look at this one while the other one's running. So this one is about the throughput. So what is my request per second? In case of the JVM one, I'll again put it in that comparison sheet. So this is about roughly 33,000 requests per second versus in the native image case, it's roughly there, right? It's around the same thing. It's around 35. So for with better startup time, lesser number of CPU instructions, better CPU, you're not trading off anything. Like you're not losing your throughput or you're not losing your latency as well. So, oh, sorry, do you want to take the picture? Okay. So the point is, even latency, if you look at it, around 5 to 9 milliseconds is, there's not much there, right? The native image is slightly better, but there's not much going on in terms of latency in both the case. So the idea is with native image, you get better CPU, better startup time, better memory, better startup time without compromising throughput and latency. And if you want to do even better in terms of throughput, we have profile guided optimizations, which will optimize that binary even more. So I'm going to skip that, and if there's time at the end, I'll come. This is, I just wanted to quickly give some quotes. This one is from Disney Streaming, and they were running a Lambda function with 3 gigs, took about 3 seconds to start with the JVM AWS Lambda, and started around under 100 milliseconds with native image. And also what they said was it was able to reduce their memory size and cost, because everything in the cloud is based on memory, right? You're paying by memory. You bring down the memory and the time that it's running, you will save the cost. Similarly, another case study from GraalVM at 10-minute mail, 30-second startup time came down to about 3 milliseconds, 6.6 gigs of RAM came to about 1 gig. Let's talk about the other two benefits. One is the security. So as we saw in the native image case, we are removing a lot of unused code, right? So we've removed anything that was not reachable at build time. So your attack surface has already been reduced, because anything that is dead, not reachable, is out, right? Classes, methods, field, everything. By default, deserialization, class loading is disabled at runtime, which means your application cannot load some random classes because of some vulnerability in some third-party library. So you are already protected. Also, JIT compiler attacks, this native executable is not affected by that, because we are doing ahead of time compilation. We don't do any JIT. We don't have JIT infrastructure in the binary. And last one is the software bill of materials, which is nothing but an inventory or a list of all the third-party libraries and their dependencies and which versions and so on, so that you can feed it into SBOM or security analysis tools, and they can tell you what's vulnerable versus what's not and so on. The advantage that you get with native images, because we know exactly which methods, which classes, which fields from which libraries, we can drill in a lot more than just looking at the jar file and treating the whole jar file as vulnerable, right? So that's the advantage. Compact packaging, obviously, as you've seen, right? We remove everything that's not there. We have a subset of the Java packages, only what's used by your application. So we're able to reduce the size. We also recommend some linking options so that you can build static executables and package them in the container images, small container images. So I'll spend 1 minute on this. There are 3 modes that we support. One is called the fully dynamic. This is that by default, this is the mode that you'll get with native image. So you get your application machine code in the binary. So the binary is only that, the application machine code. And for everything else, we depend on the operating system. So there'll be some standard C++ libraries, zlib, libc to run your application, etc. We pick that from the operating system. This is the fully dynamic case. On the other spectrum, on the other side of the spectrum is a fully static binary, where we package everything along with your native executable. So if you pass in a parameter to the native image build tool, it'll package the whole thing as a static, fully static binary, and then you don't depend on anything from your operating system. You don't need any libraries from your operating system. So you can take this binary, put it in a, as a small image, as a scratch image, for example, and run that as well. And then in the middle, what we have is the mostly static, where we only need the libc from the operating system. Everything else is in the binary. This talk is on YouTube. I won't spend much time here, but the gist of this was, one of our colleagues took the Java 18 simple web server, which is a Java application, ran it as on the JVM. So the red bars are running it on a JVM, and then the green bars are trying to convert it into a native image and run it with the various linking options. And he was able to bring down the size of the container to about 19 or 20 megs, right? The 5.45 is, I think he's running some additional UPX compression, but if you ignore that, coming down from 383 megs to 19.4 megs. And it's a fully functional web server, so it processes requests. Similarly, you can take other applications as well. So a couple of things. So yeah, we talked a lot about static analysis and all of those. So how does it work with reflection? So remember, like, you have to give everything to native image tool at build time. There is some configuration that you'll have to do for native image. So there are 2 modes. One is there is a tracing agent that the GraalVM provides, which will run through your application, figure out and create these configuration files for you. And the other one is you can use frameworks for native image. There's also a third open source framework. Sorry, there is also a GitHub repository where we have a bunch of third-party libraries with their reflection and dynamic configuration files already available. And the GraalVM build tools will refer to these files and then use them in the build dynamically. We recommend using a framework like Spring Boot, Micronaut, Helidon, Quarkus. It'll make your life easy. They've already integrated with us. This is a picture of all the 4 leads with us at the GraalVM event. Before I wrap up, I think I just want to leave with 2 slides. This is memory efficiency published by Quarkus and Helidon, about 80% lower memory consumption, 50% less memory. And the startup times were 98, 97, 94, hardly anything to choose from. I've already shown you what Micronaut is capable of, but this is the others, right? And yeah, summarizing the benefits: memory efficiency, startup time, attack surface is lower, and small size of the binary. You can go to graalvm.org, download it. We support SDK man, GitHub Actions, container images, Paketo build packs. There is also script-friendly URLs if you want to directly download in scripts. And that's it. Okay, thank you.